Hello students, I hope you're having a wonderful day. So today I would like to complete a problem with you. We're going to calculate the orbital time period of a satellite orbiting Earth, and we are given the altitude that the satellite is orbiting Earth at. So let's go ahead and get started. I'm going to read the problem to you. I'm going to list some knowns. We're going to list some unknowns. We're going to draw a simple picture, and we're going to write down our base equation so we can calculate our orbital time period. So a satellite orbits Earth at an altitude of 9.1 times 10 to the 5th meters. The mass of Earth is 5.97 times 10 to the 24th kilograms. Calculate the orbital time period of the satellite. So let's go ahead and draw a simple picture. So here we have Earth. Okay. All right, and we need to identify the radius of Earth, which I'm going to identify by r sub e, so the radius of Earth. This is 6,380,000 meters, and the problem tells us that the satellite is orbiting Earth at an altitude of 9.1 times 10 to the 5th meters. Okay, so altitude, remember that represents the position above the Earth's surface. So altitude is equal to, so 9.1 times 10 to the 5th meters, this is going to be 910,000 meters, okay? So the mass of the Earth, let's write down this, mass of the Earth is going to be 5.97 times 10 to the 24th kilograms, okay? And what we want to do is calculate the orbital time period. So this represents the amount of time that it takes the satellite to orbit Earth, okay? So our base equation here is orbital time period of the satellite is equal to 2 pi times the square root of the average orbital radius cubed divided by the universal gravitational constant multiplied by the mass of the Earth. Okay, so I've got 2 pi, average orbital radius cubed. So we're not given our average orbital radius. What we're given right now is the radius of the Earth and the altitude above Earth's surface. So this r represents the center to center distance. So we have the center of the Earth to the center of the satellite. So this r is equal to the radius of Earth plus the altitude. Radius of Earth is 6,380,000 meters plus our altitude is 910,000. Yes, 910,000 meters. Okay. All right, and so this is going to give us, what are we looking at? We're looking at 7,290,000 meters. Okay. Let me check that. My mental math might be a little bit off here. Oh, okay. All right, so we're looking good. So this r, so underneath my radical in the numerator, now remember we do need to cube this value, okay? So in my numerator, 7,290,000 meters, quantity cubed, okay? We cannot forget our cube here. We're going to divide this by the universal gravitational constant, which is identified by capital G. This is 6.67 times 10 to the negative 11th, and we have units of Newton meters squared per kilogram squared. We're going to multiply this by the mass of the Earth, which is 5.97 times 10 to the 24th kilograms. Okay, so let's take out our calculator here. Okay, so orbital time period. of the satellite is equal to 2 pi. Let's take care of our numerator first. I have 7,290,000. We're going to cube this value. We get a very large number, 3.8742 times 10 to the 20th. So not only are we cubing our numerical value, we're cubing our unit value too. So this is going to give us units of meters cubed. Okay? We're going to divide this by the product of the universal gravitational constant and the mass of the Earth. That's going to give us 3.98199 times 10 to the 14th. Let's take a look at the units here. I've got Newton meters squared per kilogram squared multiplied by units of kilogram. Algebraically, we know that this is kilogram over 1, so I've got a kilogram in my numerator here. I've got kilograms squared in my denominator. One of our kilograms is going to cancel, okay? So I've got Newton meters squared per kilogram, okay? Now let's go ahead and complete the division underneath the radical. Okay, so what we have here, I'm going to continue on up here. Orbital time period of our satellite is equal to 2 pi times the square root of 972,930.62. Now we need to take a look at the units here. So in my numerator, I have units of meters cubed. We're going to divide this by Newton meters squared per kilogram, okay? Now, we know the old algebra rule that says whenever we divide fractions, it's like multiplying by the reciprocal of our denominator. So let's go ahead and do that first. So what I have is meters cubed over 1 times the reciprocal of our denominator. This is going to give us kilograms divided by Newton meters squared, okay? So we've got 2 of our meters are going to cancel. I've got meters cubed here, meters squared in the denominator, okay? So this is going to give me meter times kilogram divided by a Newton. Now what we want to do at this point is we want to break down the unit of a Newton. You know that a Newton is a kilogram meter per second squared. So what I've got is meter kilogram divided by, let's break this Newton down, so I've got a kilogram meter per second squared, okay? So once again, we're going to divide fractions here, so we're going to multiply by the reciprocal of our denominator. This is going to give me meter kilogram over 1 times second squared over kilogram times meter. So as you can see, we have a meter times kilogram in the numerator here. We have a kilogram times meter in our denominator, so our kilograms cancel, our meters cancel, and that's going to leave us with units of second squared, okay? So things are looking really good for us, right? Because whenever we take the square root of this value here, remember, we have to take the square root of the numerical and the unit value. So the orbital time period of my satellite is equal to 2 pi times, we're going to take the square root here, so I'm just going to use some parentheses. So that's going to give me 986.372. The square root of second squared is going to be seconds. Okay? I'm running out of room here, so I'm going to go ahead and erase our unit cancellation here. So this value times 2 pi, and remember, when you're completing these problems, you always need to use the pi key on your calculator. Don't just take a shortcut and say times 3.14. Okay, let's use the pi key. So 986.372 times 2 and then times pi is going to give us 6,197.56. And we have units of seconds here. Now what let's go ahead and do is use some dimensional analysis and convert from seconds to minutes and then from minutes to hours. Okay? So what we have here is 6,197.56 seconds. We're going to multiply by a ratio that is going to cancel the units of seconds. And so we know that there are 60 seconds in 1 minute. So I'm going to place the units of minutes in the numerator. So I have 1 minute divided by 60 seconds. Right here we have seconds over 1, so seconds in the numerator is going to cancel with seconds in the denominator, leaving us with units of minutes. So this value divided by 60 is going to be 103.29. Orbital time period of the satellite, 103.292 minutes. Okay, and now we can convert this from minutes to units of hours. So we know that this is going to be greater than 1 hour and less than 2 hours, because we know that there are 60 minutes for every hour. So orbital time period of my satellite is equal to 103.292 minutes. There are 60 minutes in 1 hour. And once again, we're going to perform some dimensional analysis here. So I'm putting units in my denominator over here because it needs to cancel with my units of minutes in my numerator. We have minutes over 1. So minutes cancels out. So we're going to divide this by 60. And I have orbital time period of my satellite is equal to 1.721 hours. Okay? So remember, the orbital time period represents the time that it takes for the satellite to complete one rotation or an orbit around the Earth. Okay? Well, I hope I have helped you out today, and I hope you have a great day. If you have any questions, please give me a call or contact me by email or Canvas. Have a great day.